Body. So, good afternoon, everybody. I am Pallavi Roy, an analyst in LogHub AG. And today I'm very grateful that I'm part of this event. So this is my first time as a part of the event like this. So let's just, get started with the presentations and everything. Can't wait. Yeah, thank you. Maybe you guys can continue.
Yeah, thank you, Pallavi. Good afternoon, everyone. We OpEx, the Operations Club of IIM Nagpur, welcome you to the finale of OpMach case study competition in collaboration with LogHub. LogHub is a Swiss-based technology company providing data-driven supply chain solutions based on cutting-edge technologies. They offer products such as supply chain apps, and Office 365 add-in, and Supply Chain Ana, an analytics and automation platform. OpEx strives to bridge the gap between what students learn in classroom sessions to the practical or real-world operations through quizzes and case study competitions. One such initiative is OpMach, the flagship event of OpEx. This year, OpMach is being conducted as a part of Tangerine Trails, the annual management fest of IIM Nagpur. The event tests participants on their operations knowledge and enhances their managerial instincts to solve real-world problems through well-curated rounds involving quiz and case submissions. The competition has received the participation of 490 students from Premier B schools across the country. Teams competed in a preliminary quiz round and a case study round to reach the finals. After the evaluations of submissions from the case study round, we have 6 teams across various institutes presenting their case solutions today. Today we have with us 3 panelists. First, we have with us Mr. Ritik Luthra, MD LogHub India. Mr. Luthra is an experienced executive in the supply chain industry. His product portfolio is varied from logistics to supply chain analytics and optimization. We also have with us Ms. Pranjali, Partners Manager, LogHub India, having an experience of more than 14 years. She has a combined experience in banking, e-commerce retail, shipping, insurance, logistics, and supply chain industry. The next panelist we have with us is Ms. Pallavi Roy, Business Analyst, LogHub. Ms. Pallavi is a creative professional with proven marketing skills. She has an experience for working for a diverse group of organizations and clients. We are very glad to have you all today with us. At IIM Nagpur, we strongly believe in creating a sustainable environment. Keeping up with this tradition, we would like to present you a unique living and breathing gift that reflects our ethos and something that will live on for several decades. A tree has been planted on behalf of LogHub in the Sundarbans National Park, West Bengal. The email with the certificate for the same will be shared with you shortly.
That's really nice. Thank you so much.
Yeah.
That's a surprise. Thank you.
It's very nice initiative. Really appreciate it. Thank you.
Okay, so now I will run the participants through the rules of the presentation round. So firstly, each team is expected to be present in the waiting room prior to 10 minutes of their slot time. Secondly, the total time available for each team is 15 minutes, wherein the presentation will be of 10 minutes and 5 minutes for the Q&A post the presentation. We have Pradyumna with us, who will be keeping a track of time. You will receive a message alert on the chat box post 8 minutes and a final call at the completion of the 10th minute. No team will be permitted any additional time. In case any team joins late, the delay in their joining will be deducted from their presentation time of 10 minutes. The teams are also expected to have their cameras on throughout the meeting. So without any further ado, let's begin the presentations. So I would like to call upon Team MSG from IIM Lucknow to present, and in the meanwhile, all the other teams are expected to log off from the meeting and are expected to join back in their respective slots. So all the best, team.
Can the organizers let me know if they can hear and see my screen?
Yes.
Okay, thank you. So, uh, hello and good afternoon to the members of the jury. We are Team MSG from IIM Lucknow and are delighted to be here for the finals. I'm Grishma and my team members are Sanket Verulkar and Mayuri Vanre. Coming to the problem statement, our main objective is to reduce the total logistic cost, and to achieve that, we need to minimize the transportation and warehousing costs. For that, the optimum location of the RDC or warehouse needs to be realigned in the distribution network so that the distance is optimized between the intermediate locations. The roadmap shows the steps as to how we have broken down the problem statement to reach our recommendation. In the first step, we have selected the favorable number of RDCs and warehouses to be mapped. In the second step, this is where the distribution network needs to be adjusted according to the location's proximity as per the reduced distance. In the third step, the optimum location of the RDC or warehouse needs to be calculated. And lastly, to minimize the transportation and warehouse costs. Coming to the value chain, the given data contains 3 factories at Bangalore, Kolkata, and New Delhi, which transfer the products to 4 regional distribution centers, then to 15 warehouses, which are then transported via tertiary locations to reach the end consumer. 3 different product categories are produced at 3 different factories, that is furniture, electronics, home and kitchen products. From the given data, we have identified the 4 shipping modes: premium, same day delivery, standard and standard plus. The minimum sales quantity was 1 and the maximum sales quantity was 15 orders. There are 5 transportation methods whose volume and weight has been calculated and mentioned in the table, with the full truck load cost identified from the data. To reach our solutions, we found that the RDCs and warehouses weren't mapped as per the minimum distances, and we have calculated the location coordinates of the RDCs, which would ensure minimum cost. For some warehouses, the observed capacity was far greater than the required amount, which would lead to inefficiency. These opportunities were identified to be optimized. Now Sanket will take it over from here.
Thanks, Rishma. Can we move to next slide? Yeah, cool. So the overarching objective here of our solution is to realign the distribution network to minimize the warehouse and transportation cost. Our distribution network has 3 levels: factory to RDC, RDC to warehouse, and warehouse to the end consumers. Thus, in order to minimize the cost, we would try to reduce the cost at all the 3 levels. This cost minimization can be done through warehouse capacity readjustment or transportation cost minimization. And our analysis revealed that the transportation cost reduction has a much larger impact on the overall cost. Hence, we decided to realign the distribution nodes to minimize the transportation distance and hence the cost. We have followed a methodology where first we optimize the tertiary distribution around the warehouse by reassigning the end customers to the closest warehouse, and once the tertiary distribution has been dealt with, we move to the secondary distribution. We have a check here that the load across the warehouses should not be significantly different from its earlier capacity. Next slide, please. Grishma, can we move to
1 second. No, it's yeah.
There's a lag, I guess. Okay, cool. Yeah, so in the given data snapshots, you can see a demonstration of what we have talked so far. In the table 1, we have assigned the closest warehouse to a given city, and combining this part with the past sales data, we were able to calculate the required transactional capacity for each warehouse. In the next snapshot, we can see that when our new allocated warehouses were mapped onto the past orders, we can see that for some of the orders, there's a potential to save on the transportation cost. Now, Mayuri will take it over from here.
Thank you, Sanket. Grishma, can you move to the next slide? As Sanket has just explained, we have moved from tertiary distribution to the secondary distribution, where in the secondary distribution, we are trying to optimize the distance between the RDC and warehouse. According to the given data, we found out that the mapping of various warehouses were done to the multiple RDCs. To make it optimized system, we tried to find out the minimum distance of each warehouse to the RDC in a bottom-up approach and tried to map one RDC to one warehouse to make the transportation more efficient. Here we found out that Andhra Pradesh, Assam, Bihar, Madhya Pradesh and West Bengal had the minimum distance with Bagamari RDCs as compared to the Ghaziabad, Godhra and Kolhapur RDC. So one cluster was made for Bagamari RDCs and these 5 warehouses were assigned to the Bagamari RDCs. After assigning this cluster to the RDC, we have a one concern that because of this reassigning, are the capacity load in the warehouse being increased? To our surprise, we found out that because of this network redistribution, the capacity load in the warehouse was reduced to an extent of 20% in terms of Madhya Pradesh. So this clustering helped us in reducing the transportation cost as well as reducing the load on the warehouse, plus rectifying the issue that different RDCs were assigned to one warehouse. Grishma, next slide, please. After optimizing the minimum distance between the different nodes of the network, we tried to relocate the RDC as if that would be optimizing the complete system. As I've already explained, that we tried to cluster the various warehouses present in located to the RDC. So if we relocate the RDC to a position where all the warehouses are at a minimum distance and almost an equal distance, that would optimize the system. So here we used a approach where if the RDC is located at the centroid of the cluster, this objective can be achieved. So as you can see in the table, we changed the coordinates of the RDC according to that. For doing this, we took assumption that the geography is plane. But again, changing the RDC to a new location is a capital intensive decision, and this would need an assessment. So this we want to comment that this solution can be taken as a long-term solution. Next slide, please. Coming to your conclusion, I would like to summarize our complete solution that we wanted to give for this complete operation. First, we tried to optimize the complete system in terms of minimum transport distance that would reduce the cost of the transportation. That is the major part of the cost that we are incurring for the supply chain. We first remapped the cities to the warehouses and then went on to do that for the RDCs and warehouses. We made different clusters of the warehouses that are mapped to only one RDC to rectify the issue that different RDCs are mapped to the one warehouses. After completing the complete remapping of the network, we tried to evaluate the impact of this new network. To see that, we use the already present order data. We found that because of the new network, 21,000 orders, that is 10% of the complete order of 21,000 was impacted. And because of that, we were saving in the massive amount of 3 crore transportation cost. This remapping can help in saving the transportation cost as well as having an efficient and network of the nodes. These solutions were which can be implemented immediately. In a long-term goal, we can change the position of an RDC, like we can change the location of the RDC at a point where RDC will be located at the centroid of the cluster of the warehouses that we have made to make the system more efficient. Thank you.
Is it okay if we ask some questions?
Yes.
Right. So first of all, excellent work, guys. I do have some questions regarding the process that you have followed. So for the starters, I realized that you have started working on tertiary movement first and then went to secondary and primary. Any particular reason why you have chosen to start with tertiary?
We actually took a bottom-up approach that as we have clustered that RDCs are mapped for all the factories. So that is why we try to go on with the bottom-up approach that the city's minimum distance to the warehouse, then minimum distance to the RDC.
Okay, so that approach is correct. So if you have started with tertiary movement first, that approach is correct. The reason for that approach, why you should always, and this is just an additional information, the reason why you should always start with tertiary movement is because tertiary movement involves the customers which are controlling the demand. So all the demand is being controlled only by customers, not by factory, not by warehouses. And hence you would optimize the warehouses which are serving to the customers first. Second question is, can you go to the slide wherein you had the previous old realignment and new, I don't remember which slide is that, but I saw it somewhere. Right, the capacity realignment. So these are the remapping of RDC to the warehouse. And when you say that the realigned capacity has been reduced, I would assume that it would be adjusted to any other warehouse. Is this the case that is happening?
Yeah, that is what happened.
So can you tell me the warehouses which have increased capacity than the old capacity?
So I
Uh,
think in the last slide we have highlighted the warehouses for which the capacity is reduced, but we haven't highlighted the warehouses for which it has increased.
That is
yeah.
fine. That's fine.
Yeah.
So my question here is, whenever you would do this analysis, you are the major criteria that you're considering right now is distance, and that is correct because that directly impacts the cost because you have a transportation cost involved. But you have one more cost involved in this picture, and that is the warehouse cost. What would happen if the warehouse which sees increase in capacity has more cost involved to it than the one which sees reduced capacity? Wouldn't that increase the overall cost?
Yeah, so we took that into consideration because let's say the capacity will impact the variable cost, right, for the factory, or sorry, for the warehouse. But
Mhm.
when we did the calculation in the Excel, we found out that that cost is comparably lesser than the transportation cost,
Mhm.
and the impact created by that cost is way lesser than this. That's why we avoided that calculation and focused on the transportation part of it.
Got it. And one last question from my side. Can you go to the slide wherein you propose the new coordinates for the warehouse?
Yeah.
This is the one.
Yes.
Do you know what this analysis is called?
No, not really. Actually, I read a research paper about it, and from there I got the algorithm, but I don't know the name for it.
It's called the Barry Center analysis or a center of gravity analysis, and excellent work incorporating it in your solution.
Thank you, sir.
That is it from my side. Finally, over to you.
No, nothing much. I just wanted to understand. When you were working on this project, you have already had your as-is cost, current cost already somewhere, because you would have compared your output to tell that that there is improvement in cost. You would have some cost that you would start off with. So,
Yeah,
do you have that calculation?
yeah, it is there in the Excel, and we have put a snapshot of that. So, Grishma, can you move to slide number 6?
Okay. Yeah, here.
So here we have mentioned both the cost. The minimum transportation cost is the cost with the current system, and their transportation cost with the new system is also mentioned there. So for the rows which are highlighted in green, we are suggesting that the cost has reduced with the new system.
Okay, so the one that you answered, Ritik, that in warehouse cost you've not made any changes then, correct?
Yeah, yeah.
But if the capacity of the warehouse would increase, will the cost change over there? So will that also impact the overall costing?
Actually, we had a constraint here that the cost of warehouse capacity was not given in the case. So we were not able to evaluate that. We just evaluated that the how the capacity load would change for a warehouse. And as said that we tried to see that the capacity is not changed significantly high, that would impact the transportation cost.
Yes.
Okay, okay. So that was all from my end, and yes, really nice presentation. I liked it.
Thank you.
So that is all, Pallavi, at least from me and Ritik.
No, I really like the presentation. And yes, we can move forward with the second team then.
Right, the second team is already in the waiting room. So
First team, thank
Yes,
you so
thank you so
much.
much.
Yeah,
Yes,
Thank
thank
you.
you.
It's kind of
afterwards, let the second team join in. Yeah, thank you. Thanks for your time.
the second team to present is Team Happiest Mind from NITI Mumbai. So good luck, team.
Yeah. So just to add, I would like to ask you guys a question. Do you mind asking you questions in between, or just we should park it for the end? So how would you like to counter the questions?
Anyway, panel is comfortable with. We can go anyway.
Okay, okay. Thank you. Thank you. Best of luck then. Yeah, continue.
Thank you. So I would be presenting. Is it visible now?
It's loading. It's not yet. At least I can't see it yet.
No, it's still loading. Maybe
You can
Kuldeep,
just
you
stop
can
and start
Yeah,
again.
yeah.
Wait a minute. Is it visible now?
No, it's not yet. Yeah, it's
Yes, now we can. Yeah. Go ahead.
So Piyush, you can start now.
Okay. Good evening, judges and my fellow mates. My name is Kumar Piyush, and I am going to introduce with the problem statement and introduction what we have just incurred with the cases. Next slide, Prajapati. Kuldeep. Next slide.
Is it changing? Maybe it's a lag.
Yeah. So basically, with the cases that we have given, there are 3 factories and 4 regional distribution centers and 15 warehouse. And using the concept of operations research transshipment models, we need to design or optimize the transportation costs that include the logistic as well as warehouse costs. And plus another questions that we also need to reallocate the regional distribution centers, like what is the optimal method, so what is the optimal way so that we can minimize the logistics cost. Next slide. Kuldeep, next slide.
I think there's a lag on his system.
I think there is a connectivity issue, so I will be presenting the slide.
Okay.
Okay. Can you please confirm if the slide is visible?
Yeah, that is
Yes.
visible.
Yes, yes.
So moving directly ahead to the selection model. Mema, can you just switch on next slide?
Okay.
The select model slide from where the Prajapati is going to take over.
Okay.
Yeah, Prajapati, carry on from this model.
So the screen is not visible.
Yeah, you can carry on with the model that you have.
So model we have selected is a linear programming model for the optimization, and software we are using is EMPL software, which we have learned in our academic course. And the solver we are using in this software is a Groovy solver, which is used for linear programming itself. So we have taken the concept of vehicle routing optimization, which determine the route of fleet we are going to use at the minimum cost. So our objective function is to minimize the total variable cost of RDC, total variable cost of warehouses, that total fixed cost of warehouses and RDC as well. Along with that, the transportation cost, which is going to carry out between factory to RDC, RDC to warehouses, and warehouse to tertiaries. Next slide, please.
Mema, go to next slide.
So our model has basically 3 things which is required: basic parameters, decision variable, and the objective function. Basic parameters are as follows, like the distance between the factory to RDCs, distance between RDC to warehouses, and distance between warehouses to tertiary. Then demand at the tertiary points, because anyhow we are going to meet the objective of meeting the demand. Along with this, we have the fixed cost at the RDC. If we are going to transport any single unit from that RDC, we have to incur a fixed cost. So we have taken it as a in consideration for binary variable. Then we have also considered a capacity at warehouse at RDC, because if we are not considering any capacity at particular point of location, then it is going to infinite its capacity. Next slide. So coming to the problem formulation, we have taken the weight as a variable, like whatever the weight we are going to assign on a particular path. Then also we have initially we have to take weight in different categories, because we have to meet the demand in categorical position. After that, for the transportation purpose, what we can do is we can aggregate the category load at the particular path. So again, I have taken it as a variable of aggregating the categories. Next slide. Now at this moment of time, at this moment of code, what I have done is initially I have optimized the weight transportation from factory up to the tertiary point. Now I have two ways of solving it. One I can do is divide the weight transported by the capacity and assign the vehicle. But while doing this kind of scenario, its model is getting converted into non-linear model, and it is very difficult to solve the model by non-linear process. So what I have done is, here I have taken vehicle also as a variable thing and applied a constraint, like whatever the weight is going to be transferred on a particular location, and the capacity of vehicle assigned on that location should be greater than the total weight. So in this way, I have formulated this problem in a linear manner only, but it has increased my number of variable. Next slide. These are the output part. So Mahima, could you?
Okay. So coming to the output, as Prajapati has told, we have used the ample, and using Groby solver, we have found the objective function here. So actually, we interrupted the ample output after 3 hours, after 10 lakh 52 iteration, and we got around 79 crore as an objective function. So as you can see, we arrived at the variable cost of all the various RDC according to the weight that was getting transported from the factory to the RDC, and we also arrived at the variable cost of the warehouse according to the weight that was getting transported from the RDC to the warehouse. And using this code, we also arrived at various other variables, that is total variable cost of the RDC, total variable cost of the warehouse, and the total fixed cost, as well as we arrived at the transportation cost of the all three different nodes, that is from the factory to RDC, from RDC to warehouse, as well as from the warehouse to the tertiary. Besides this, we got various insights. First was we were getting insights according to the all the three category product category, that is electronic, furniture, and home and kitchen appliances. Uh, in all these categories, we were able to arrive and get a solution that which factory should supply to which RDC, as well as which RDC should supply to which optimum warehouses. As you can see in this picture, the output, for example, the RDC is supplying the material to warehouse. But if we see the example that Bagmari RDC is supplying to Gujarat, that is in the power of e to the power minus 10. Because since we have interrupted the ample code after 3 hours, so we are getting this solution. If we would have allowed the ample code to run for several hours, we would have got the value 0 here, because we have put the constraint accordingly. One of the main insights was that we got which warehouse was operating and which warehouse was closed. So we were getting that Assam, Bihar, Kerala, Punjab, and Tamil Nadu should be closed. So I would like to end our presentation, and I would like to open for questions. Thank you.
Right. Um, Thank you for the excellent presentation. I do have a couple of questions here. So if you can go to the slide wherein you were defining the variables.
Okay, yes. Just a second.
Yep. Right. So how did you define the fixed cost of the warehouse in the variable?
So for this, I have taken a binary variable like fixed cost of RDC, FCRDC, and could you change the slide, please? Next slide.
Yes.
So this is the variable FCRDC and FCWS. These are the binary constraint here. Okay, so this is going to take a value either 0 or 1. In constraint, what I have taken is this binary number is multiplied with the capacity of RDC. So if particular RDC need to transport from there, they have to take the binary variable as a 1, and it is considering the fixed cost of that particular RDC or warehouse respectively.
Okay. So does that mean that if there is a particular warehouse which is not transporting any material, you would consider the cost of that warehouse as zero?
Yes, because that warehouse we are not going to operate, so there is no fixed cost we are considering over there.
Okay, and as an outcome, these are the warehouses that you had suggested should be closed at the end. That's how you
Yes.
define. Oh, okay, good. Second question is, whenever you were considering the transportation cost, I remember you mentioning the transport capacity of the vehicle being a variable as well. How did you take that variable into consideration, and what constraint did you use there?
Capacity is fixed, but the number of vehicles are kept as a variable because we have two ways of calculating the number of vehicles. Either I will calculate total quantity by their capacity, but in this way, model is turning into non-linear. So what I have done is I have allowed my model to decide the number of vehicles as a variable. What he is doing is one side he is taking total weight, one side he is taking total number of that vehicle. So if we multiply vehicle into its capacity, then that amount should be greater than the weight going to be transferred from there. Although we are minimizing the objective, so it is not going to take very much number of vehicle because in directly it is going to increase the cost. But constraint is total capacity should be greater than equal to total weight on the particular path.
So in the real-time scenario, let us say you have warehouse number one, which is transporting, let's say 15 tons of material, and you have 5 options of the vehicle that is required. The model would compare the total capacity to be shifted out of that warehouse, and that should be, and the vehicle capacity should be greater than that, and then it would choose that vehicle and consider that cost. Am I correct?
Yes, and cost is going to be minimum. Well, whatever the combination it will be, cost is going to be minimum.
So you have considered cost as a variable function as well, is it?
In objective function, I have taken as a cost, but in variable function, I have taken only number. So when it is defining the number, objective should be considered as a minimum only. So whatever the combination he will try to make, he will be on the objective of minimum cost only.
Okay, so he's taking the number, the model is taking then the number, multiplying it by the cost, and the objective is considered as minimum cost, and that works as a
Yes.
constraint, and then it would take.
Yes.
Okay, good.
Yes, yes.
All right, that is all from my side. Anjali?
No questions from my end.
Pallavi?
No, Ritik, thank you. Hello, team. Great teamwork. Thank you for your time. Let's just welcome the third team for today. And yes, you guys can join in afterwards then.
Yeah, good
Thank you,
work, guys.
Panda. Thank you. Thank you very much.
Thank you.
The next team to present is Team Achievers from NITI Mumbai. Good luck, team.
Hello, Team Achievers.
Yeah, hello, ma'am.
Yeah.
Shall we start?
So we will not interrupt you in between. You guys can carry on with your presentation part. The questions we will ask you in the end. Yeah.
Okay.
Best of luck. Carry on.
So, can someone please confirm whether screen is visible?
Yes, it's visible. Yeah.
Okay. So, hello everyone. Firstly, I, on the behalf of the team Achievers, would like to thank you all for giving us the opportunity to present our case analysis. Next slide, Jatin. So, this is the basic model as given in the case problem. Like we were given 3 factories, 4 RDCs, and 15 warehouses. And the problem statement was either we can realign the supply chain or whether some RDC or warehouses should be omitted in order to optimize the total logistic cost. So what we have done is we have evaluated three things to our optimization model. That is, which factory should supply quantity to which RDC, and from which RDC it should be supplied to which warehouses. Second thing is how much quantity should be transported, and third thing is which type of truck should be used. That is, we are given five different types of truck, that is 32 feet SXL, MXL, 22 feet, 14 feet, and Bolero pickups. All these three things we have evaluated through our model. Next, Ajit. So while solving our model, we have taken certain assumptions. Like first one is we have solved our model through AMPL, as Excel was not capable of solving so much constants in the variable. So we have used AMPL, which is an algebraic modeling language used for large scale mathematical computations that allows you to describe and solve high complexity issues. Second thing is we have taken into account only full truck load in order to exploit the economies of the scale. And third thing, what we have done is we have collated the sales data of 1 month for different warehouses and accordingly found the total logistic cost for 1 month. And fourth thing is that as truck capacities was not given to us, so we have taken into account some assumptions like 32 feet SXL is capable of holding 7500 kg and 32 feet MXL is capable of holding 15,000 kg. Similarly, 22 feet 4500 kg and 14 foot 3500 kg, and Bolero pickup is 1700 kg. And we designed our model in such a way that set of code remains same, but the data for three different factory changes. Like the model remains same, but we have designed three different supply chain for different factories. Like for Bangalore factory, we have to feed the data into our model, and the optimal solution will be given. And sixth thing is factories are assumed to have the capacity that can fulfill the required demand, and volumes of the items are not taken into account for a calculation. We have considered only the weights. And last thing is that we have not taken into account tertiary distances, and that was complicating the whole problem as the number of constants and the variables was increasing. So next slide.
So this slide basically shows the codes that we used for our optimization model. Basically, we use the mixed integer programming and the transshipment model for the optimization of our supply chain. So as you can see on the left, there are the parameters that we used. The parameter S basically represents the supply capacity that can be fulfilled by the different factories. Parameter D basically represents the demand requirement at the different warehouses. Parameter FC1 shows the fixed cost of the different RDCs. Parameter FC2 represents the fixed costs of the different warehouses. Parameter VC1 represents the variable cost of warehouses. VC2 similarly represents the variable cost of warehouses. Parameter TC represents the truck capacity which we assumed for different truck types. Parameter distance represents the distances between the various sources and destinations. And param cost represents the transportation cost between the different locations. In the top, you can see the objective function. So our objective function consists of like total cost, which we needed to minimize, and it consisted of the fixed costs of the warehouses that will be open, fixed cost of the RDCs that will be opened, their respective variable costs, and also the transportation costs through different truck types. Below the objective function, you can see the variables. So variable X represents the basically quantity in kilogram that is transported from the different factories to the RDCs. Similarly, variable Y represents the quantity shipped in kilogram from the RDCs to the warehouses. Variable XB is the binary variable, and it basically represents whether a particular RDC will be opened or closed. Similarly, variable YB is also binary, and it represents whether a particular warehouse will be opened or not. Variable TQ represents basically the quantity of the shipment that will be transported through a particular truck type, that is 32 feet multi-axle or 22 feet or Bolero. At below, you can see the various constraints that we provided to our model. First one is the supply capacity constraint, that is the different factories, the quantities that they can supply, they must be less than or equal to their capacities. Second one is the demand requirement, that is the demands at various warehouses, it must be equal to the demand requirement. Third one is the node balance, that is at the RDCs, whatever material we are getting, it must be equal to whatever material it is transporting to warehouses. And in this case, we can have assumed a different constraint if the inventory level or the capacities of the RDCs and warehouses was provided to us. And in that case, the constraint could have been like whatever the quantities we are receiving at RDC minus whatever quantities we are supplying to warehouses from RDCs is equal to the inventory stored at the RDC. The next constraints are the big M methods, are the big M constraints that we used in our models. It is basically these are basically used so that if any of the quantity is assigned to a particular warehouse, then their binary variable should become 1, and in all other cases it must be 0. And we have formulated 64 more constraints for restricting the quantities transported by the truck to a particular warehouse. So basically, after solving our model and giving the data for the different factories, we got the following solutions. This slide basically shows the data about the furniture items which were transported from Bangalore factory. So for the furniture items, only 3 RDCs needed to be opened, that is Bhagmadi, Ghaziabad and Kolhapur RDCs. And from Bhagmadi RDC, the quantities will be shipped only to 3 warehouses, that is Assam, Bihar and West Bengal. From Ghaziabad RDC, the quantities will be shipped only to Punjab and Punjab 1 warehouses, and the rest of the warehouses will be replenished from the Kolhapur RDC. So no furniture items will be shipped to the Godhra RDC, and all the shipments are transported by 32 feet multi-axle at full truckload condition. And the total cost of warehousing as well as the transportation for furniture items comes out to be 53.48 crore rupees. Over to you, Mayank.
Thank you, Jatin. So on the similar lines as Bangalore factory, we have formulated separately for the New Delhi factories, which is manufacturing electronics items. So for the New Delhi factory, we have got that we are supplying to only one RDC, that is Ghaziabad. So there is no shipment from New Delhi factory to Godhra, Bagmati and Kolhapur RDC. And from Ghaziabad, we are supplying to all 15 warehouses. Again, we have used the FTL foot truck load with 32 feet MXL capacity trucks. The total cost of this particular factory comes out to be 5.831 crore rupees, and that is justified because here only we are opening just one, or we are just transporting to one RDC. The numbers in the box displays the number of quantity in kgs which we are transporting from factory to RDC and then RDC to warehouse. Next. Last but not the least is the Kolkata factory. For the Kolkata factory, we are supplying to 3 RDCs. There is no shipment from Kolkata factory to Bagmati RDC, but from to Ghaziabad, Kolhapur and Godhra. From Ghaziabad, there is only one warehouse we are supplying, that is Punjab 1, and from Kolhapur, there are 2 warehouses, Karnataka and Kerala, and rest of the warehouses have been supplied from the Godhra RDC. Since there are 3 warehouses, so the total cost definitely be more than the New Delhi one, that is 16.276 crore for this particular Kolkata factory. The items manufactured is the home and kitchen items. Again, the numbers shown in the box are the digits in the quantities that we are supplying. So this is the final slide. Since we have solved this model individually for each company, so there are fixed costs which have been in their model 2 times or 3 times. So we have subtracted all those costs while calculating the final cost. For example, on the left side, this is the total cost we are getting for individual factories, the total logistic cost. But since the Ghaziabad RDC was appearing 3 times, so we have subtracted it 2 times, and the Kolhapur RDC was appearing 2 times, so we have subtracted it 1 time, the fixed cost from that cost. And same goes with the warehouses, as the fixed costs associated with the warehouses have been appearing 3 times in the all 3 individual factories. So we have subtracted those cost taking multiplied by 2, and after calculating this, we have got this final cost around 73 crore 53 lakh 49,652 rupees. So this is all about the case as discussed by the Jatin earlier, that we could have also gone for similarly for the tertiary distances in the tertiary locations by creating one more balanced node of transshipment, but since the tertiary distances are more and the model is getting complex, so we have restricted our this model up to warehouses only. Thank you.
Right. Can we go ahead with the questions?
Yeah, sure.
Yeah, sure.
Perfect. So first thing is that I really like your slides. I really like how you explained the variable and constraints in AMPL, which, so I'm assuming you use the student version of AMPL, correct?
Yeah.
Yes, sir.
Second thing is, I understand that you have not used tertiary ones, but that that is fine. Whatever you have used primary and secondary, that should be good enough as long as you started with secondary, which you did. I do have one question, and this question is, this problem is pretty common with softwares like AMPL. What would happen? So can you go to the slide wherein you showed the truck being used? Yeah, this one. No, the one next to it.
Next.
Right. So here all the shipments are transported by 32 feet MXL. Any idea, any guesses why the solver chose 32 feet MXL?
So basically, Jatin, can you move to the AMPL code where it is showing the objective function? Sir, here we have formulated an objective function like for here the distance TU divided by TCU. We have what this statement sum bracket T in T comma U in U. This whole statement is about. We have just formulated like number of trips for a particular vehicle, like capacity has been divided by the transporting quantity, like transporting quantity divided by a truck capacity. This is multiplied by the particular cost of that particular truck. By this, I will be
Manchu, can I add?
Yeah,
can I add
okay.
to this?
Okay.
So basically, like 32 feet multi-axle, it has the maximum capacity, maximum payload capacity, and when transporting any kind of shipment through this truck, the number of trips will obviously be less. And so in our model, in objective function, you can clearly see that we have multiplied the cost of per trip shipment into the number of trips. So for 32 feet multi-axle, this product of cost and number of trips was leased. That is why it is transporting everything through 32 feet multi-axle trucks.
Exactly. So the only reason why the solver has chosen 32 feet MXL is because the capacity of 32 feet MXL is highest among all the transport vehicles available, hence reducing the trip, hence reducing the distances, hence reducing the cost.
Yes,
Now
sir.
this is the problem with the function like this. So nothing against the solution. You've done an excellent work on the solution. I'm just giving you some add-on information as to what happens. What would happen? So let me give you one scenario. What would happen if you have a factory in Kolkata, you have a RDC in Delhi, and you have a material that needs to be transported as 50 tons, 50 metric tons, and you have a 32 feet MXL available, which has a capacity of, let's say, 24 metric tons. How many trips would it make?
So like it's 2 trip of FTL and then one would be LTL.
Correct. So now what the system is not considering at this point of time is the LTL movement, because whenever you are considering the FTL, the number of trips would reduce because the capacity is higher. But the moment you start talking about the LTL part, it doesn't matter what the capacity of the vehicle is and how much extra material it can handle. The only thing that matters is what is the cost. And now the capacity is out of the picture, and this kind of model does not take that into consideration. So this is just a footnote from my side. Ideally, in the ideal scenario, whether you use AMPL, you use any other solver, you use any or you're doing it on Excel. Ideally, there is one more function that is required additionally for LTL, which would consider the residue weight that is coming out after the FTL movement is completed, and then comparing that residue weight on the cost to identify which vehicle to be used for the LTL movement or the remaining part of the cargo. But still, I like the presentation. Excellent work that you guys have done.
Thank you.
Thank you so much.
Over to you, Friendly.
Mine was also on the LTL portion only because I actually saw that in their assumption also they had mentioned that they have taken only the FTL movements. So that
Yeah.
was also something that I wanted to ask because we had in our case study also we have given the details about how you could calculate the LTL movements in that. So that was my question, but I think Ritik already covered everything on that front. But in all, yes, the presentation was very good. It is very detailed with all the figures and everything mentioned. So that is it's a good job on that front. Good work.
Thank you.
Thank you.
Yes, Pallavi, we are done.
Yeah, thank you. Thanks, Ritik. Thanks, Pranjali. Thanks, participants. So I agree. I completely agree with Ritik and Pranjali. It was a great presentation. And yes, thanks. Thank you for your time. Yes, let's just log in afterwards and allow the next team to come in and show their presentation.
Thank you.
Thank you.
Yeah.
Thank
Sure.
you.
Thank you, ma'am.
Yeah.
So the next team is Team Challengers from NITI Mumbai. So good luck, team.
Yeah, I will be presenting my screen.
Yeah. Hello, team. Best of luck for the presentation. And we'll ask you some questions at the end of the presentation. Uh, you may continue now.
Thank you.
Yeah.
Hope my screen is visible. Shall we start?
Yes.
Yes,
Yes,
please
yes.
go ahead.
Okay. Good evening, everyone. My name is Sai Krishna Reddy. I, along with Kalyan and Sandeep, will be presenting on the case today evening. Next slide. Before diving into the case study, I would like to summarize few of the key insights and the highlights of this case study and key points on what we have tried to achieve through this optimization that we have done. The main objective of the optimization that we have done is to minimize the logistics cost, that is the transportation and the holding cost of the current distribution network that has been provided to us. And the key main deliverable that we are trying to provide here is to identify if all the RDCs and warehouses are required, or if there is any realigning of the distribution network that needs to be done to minimize the overall logistics cost. And the major constraint that we have at hand is that each factory will be able to produce only one type of product, that is either electronics, furniture, or home and kitchen products. And the tools that we have used are Microsoft Excel, AMPL for optimization, and for the modeling, we have done the integer linear programming. The main objective of the Excel is we have tried to refine all the data that has been provided to us and to come at the cost matrices, specific sales data to come which say has which kind of sales demand, etc. So we have got that and imported everything into AMPL and did our optimization there. And few key insights from the data results that we have achieved are currently with the existing distribution network, we have the total logistics cost as 540 crores approximately. And with the optimization that we have done, we are able to narrow it down to 108 crores approximately, a total of 80% reduction in the total logistics cost. So we will be talking how we have done that in the coming slides. Next, please. For building the entire model, we have divided the total model into three stages, which are last mile network modeling and the intermediate network modeling and the first stage network modeling. And these three stages of models are highly integrated so as to produce a globally optimized solution and refrain from producing any locally optimized solution or a suboptimal solution. And the first, we came in the backward direction starting from the demand point and to the factory. Speaking about the last mile network modeling, the first step is to calculate the total demand required by each city on a daily basis. And this is very crucial because the last mile is dependent on the daily basis for allocating the vehicles. Apart from this, the vehicle allotment also considered the factor that capacity constraints on both volume and weight direction. Based on this vehicle allotment, the model will develop a probable transportation cost matrix, which is nothing but the cost that would incur if a particular warehouse will serve a particular demand point. And after these three steps, allocation of warehouse to a particular demand point is modeled as a binary decision variable. Now, speaking about the intermediate network modeling, which is nothing but the modeling between RDC to warehouse, the category-wise total demand at each warehouse is formulated as a function of the allocation that is done in the previous stage, that is the last mile network. And then for this stage, the decision variables are the demand allocation between the RDC to warehouse for each category. And then based on this allocation, we will calculate the total demand that is moving from a particular RDC to particular warehouse. Depending on the weight and volume of that demand, the model will be allocating the vehicles and the corresponding transportation cost matrix once again. This is nothing but the amount of cost per kilometer that would occur if a particular RDC serves a particular warehouse. And then speaking about the first stage networking model, here demand allocation between the factory and RDC makes no sense because there is a constraint that a factory can produce only one category of product. So if a particular RDC has certain amount of demand for a particular category of product, the entire demand has to be served by the factory that produces that product category. So the major allocation here is between the factory and the product category that is to be produced in that factory. Once that allocation is done by the model, then it calculates the total demand that is being moved from one factory to particular RDC and the corresponding vehicle allotment and the corresponding transportation cost matrix. This transportation cost matrix is nothing but the cost that would incur per kilometer if a particular factory serves a particular RDC. And then taking the total cost, transportation cost matrices of 3 stages, the distances between the points and the allotments, the holding costs at each stage, and the decision variables which shows whether a factory or whether a facility is opened or not. The total objective function is designed as the summation of all these, and minimization of the objective function provides us with the optimized model.
Now let's discuss about the mathematical model of the methodology already discussed. For this, we have used the AMPL software, and the primary objective function for this mathematical model is to minimize the overall logistic cost, that is summation of transportation and holding costs. So in order to calculate these costs, we have to input various data such as distance between facilities, transportation cost per kilometer into the model. And talking about the decision variables, all the variables are demand allocation in nature. So they are considered to be integer variables, except the last mile variable. The major reason behind it is in the last mile, the entire city of the demand is assumed to cater by only one single warehouse. So we just need to decide upon which warehouse that is. So that's the reason it's taken as a binary variable. And all this input data and decision variables are subject to several constraints, like one factory can serve only one single product category, and each city must be served by only one warehouse, whereas one warehouse has the flexibility to serve more than one city. And at any given node, the sum of inflow should be equal to sum of outflow, and total demand at any given layer should be catered by its subsequent previous layer present in the supply chain. And the AMPL code for declaring the variable, setting objective setting parameters and defining objective function can be seen in the slide. And the major reason behind using AMPL is due to the presence of larger number of variables, so that Excel solver cannot handle it. So that's the reason we have used the AMPL software. And we use the specifically we use the Gurobi solver in order to come to the optimized distribution network. So in the most optimized condition, Bangalore factory has to produce electronics, New Delhi factory has to produce home appliances, and Kolkata factory has to produce furniture category. And the respective demand allocations in the optimized condition can be seen in the subsequent tables. In the factory to RDC table shows the first layer demand allocation, that is factory to RDC, and the RDC to warehouse demand allocation product category wise can be seen in the 3 other tables. And the last mile, that is warehouse to city allocation, has not been shown here due to the space constraint, due to the presence of more number of cities, which are around 750. So that has been uploaded in the sheet. So next. So after the allocation has been done, we have calculated the overall cost, overall cost at each of the layer of the supply chain. So before optimizing, the cost was around 540 crores. Post optimization, we were able to get the optimized cost around 108 crores, which is around 80% reduction. So these tables show the breakage of all the costs at different stages. If you concentrate at the third table, that is warehouse to cities, last mile transportation cost, previously it was around 148 crores. It was now reduced to around 33 crores. The primary reason behind this is more number of majority of the variables are present in the last mile, and major optimization has been done by the solver at this stage. Next.
So now I'll quickly talk about the assumptions, observations that we have made, and some of the scope for improvement that we are trying to suggest here. Considering the complexity of the distribution network with approximately 1700 SKUs that need to be catered and 780 cities that we need to distribute, we are trying to make few assumptions to narrow down our model. So the major assumption among them is that warehouses and RDCs are replenished only once in every month. We have made that assumption based because there was lack of data on the production side as well as the allocation side. And then we also assumed that to replenish that to warehouse and RDC, only 32 feet containers are used because we are trying to optimize in terms of volume, which I'll discuss later. Those are the key assumptions that we are trying to make. And when it comes to assumptions, 99% of the logistics cost is due to the transportation cost. So we can understand like how significant that costs are, and we can try to focus more on that transportation side to optimize that overall logistics cost. So what we are trying to do is we'll have a additional distribution layer, that is hub or depots, where we can aggregate the demand of different cities, so that the amount of safety inventory that we need to maintain at different parts of supply chain can be reduced. And we can also use a concept of milk run to allocate that demand to different cities from particular warehouse. And in optimized model, what we have observed is all the facilities are used and functional. So we can also do cost benefit analysis of establishing new facilities if required. And the major observation what we did is from Bangalore factory, we are traveling towards north, that is Kolhapur RDC, and coming towards south for Tamil Nadu and Kerala warehouses. So we are double traveling. So what we can do is we can either have a storage location at factory itself and directly transport it to warehouse, or completely bypass RDC from Bangalore factory and directly transport from Bangalore factory to the particular city that in Tamil Nadu and Kerala. That completely eliminates the double travel that we are making from factory to north, again coming towards south. And finally, as I mentioned earlier, volumes are what are driving the vehicle allocation, because even we are, if we are satisfying weight, volumes are what driving the vehicle allocation. And thank you. We are open for questions now.
Thank you, everyone. Excellent present. Who made this presentation? All three of you or any one of you?
It's a team effort.
We made it as a team.
Okay, so I really like the part wherein you have explained the methodology. Can you go to that slide? Correct. So I really like this part, particular part, because this explains a lot as to how your thought process was working and how you designed the architecture of this study. So excellent work on this particular part. I also really liked how you spent a lot of time on the last mile planning and how you considered the daily weight allotment, because that is most crucial activity in the last mile planning. Which brings me to one question regarding the last mile planning. I remember somebody mentioning that in the last mile planning, you have considered one warehouse to one customer alignment. Can you elaborate a little bit more on that? Why did you consider that?
Yes, sir. First of all, we were analyzing the data given in the Excel sheet, and we found that from the current data, one particular city is being served only by one warehouse. But a particular warehouse can serve multiple cities, but a city is being served only by one warehouse. So we considered the same assumption, and based on that, we built the model.
Okay.
So adding to this point, the city demand is catered on a day-to-day basis. So that's the reason we thought of the entire demand is catered by only one particular RDC, one particular warehouse.
Okay. My overall observation regarding your solution. So I really liked your solution. I liked your solution for two reasons. Reason number one, you have, so when you do a network design activity, and whenever any organization is doing a network design activity, it is not only impacting their supply chain network, it is impacting other activity areas as well. So for example, it is impacting the inventory storage cost, production planning, etc. So it's impacting everything in the supply chain. What is happening here is right now in your situation, you also, I remember you have put up a suggestion wherein a factory can directly bypass the RDC and supply cater to the distribution center. This is also a good suggestion which impacts the inventory storage part. But whenever you are trying to explore these opportunities wherein any one particular node is bypassed, either RDC is bypassed or RDC is supplying directly to the customer, that area you're trying to explore, then such assumptions wherein one warehouse can only cater to one customer would become risky. That is point number one. Point number two, whenever you are dealing with multiple category of the products and there are different factories which are producing different category of the product, then this kind of assumption would also become risky, because now when you have taken this particular assumption, that would mean that in each of the warehouse, you would require a lot of quantity of each category of the material, and now you cannot make a category specific warehouses. But that is a completely different study. So I'm just giving you some advice for whenever you'll complete your studies, you'll go to the organizations, real-time work, etc. So these are some suggestions on that front, but your job at this point of time was to do a network design study, and you did that study pretty well. So good work on that front.
Thank you, sir. Your suggestions definitely add to our knowledge, sir.
Thank you. Finally, over to you.
Yeah, I have just one bit to check with y'all because the vehicle utilization that you have done for all the routes and everything, you have taken only 32 feet as the movement of a vehicle. Is there a particular reason why you chose that, or is that because of the solver that you have used?
No, ma'am. Actually, there are three stages, one from factory to RDC, RDC to warehouse, and warehouse to last mile. In the last mile case, we have considered all the type of vehicles possible, and they are automatically modeled. But for the replenishing warehouses and RDCs, we only considered 32 feet because we observed the data, and most of the time what happening is we assumed monthly replenishment. So the demand is so heavy and volumes are so high that normal trucks like Bolero or 14 feet or 22 feet are not enough. Even the 32 feet are very high, like 10, 5 are being utilized. So we thought we could make that assumption to simplify the model a bit. That was the main reason behind this. And this assumption was valid only for RDCs and warehouses, where the last mile was considered all the category of vehicles, starting from Bolero to 32 feet MXL.
If at all your capacity of whatever that you were transporting from your factory to your warehouse or to the RDCs, if at all it is less than the capacity of the truck, your full 32 feeder is still traveling from that place from factory to the RDC, or you have then over there thought that maybe you can use some other vehicles over there? Because, for example, if it is 45 tons that you're looking at, and if 32 feeder has 25,000 capacity, okay, then how are you managing the residue once that would be there? That would go in 32 feeder also? Is that how you're...
What we have done is we have used the current given data that is provided to us. Like we have the sales data and demand data. And from that, we have come to this assumption. If the demand is dynamic, then we would have to change that assumption. Currently, we have the data, so from there we have.
Also, adding on to what Krishna has said, ma'am, in the current model, especially for RDCs and warehouses, we only considered the full truckload. So, as you asked, if it is 45 and the capacity is only 25, we have to take another 32 feet truck of full capacity, although it is not being completely used. So we are only considering the FTLs.
Okay. Because I think if you would have also considered the LTL and if you would have calculated the vehicle cost, there were chances that maybe there also the cost saving would have come into picture. So again, that is also a footnote just whenever you all are working on any such projects.
We actually tried to that model, ma'am, but in the last minute, we don't know, some problem in the model happened and it's not working. So we have to drop one step down, assume that it's only FTL, and then proceeded with the model, ma'am.
That's nice. So as long as you already have that in your mind and you know that this is what is the right approach, then that is all that is required actually.
Thank you.
Okay, so that was all from my end.
Sorry, I do have one more question. Can you go into the cost comparison sheet really quick? Right. So when you calculated the current cost and you compared it with the the new network cost, how did you calculate the current cost?
So the current costs are calculated wholly on the same assumptions as we considered as the optimized cost, sir. For example, if we considered 32 feet trucks for RDCs and warehouse replenishment in the optimized model, we considered the same factor in the old cost as well. So the comparison is on the same level and well judged.
Okay, got it. That's all I wanted to know.
Thank
you. Got it. Over to you, Pallavi.
Yeah, thanks, Ritik. Thanks, Pranjali. Thanks, participants. Nicely answered the questions. Now I would love to ask you guys to log in afterwards and let the next team join in so that we can proceed. Yeah.
Thank you.
Thank you all.
Thank you.
Thank you all.
Let's everybody. Yeah.
So the next team up is Team Transformers from NMIMS Mumbai. All the best, team.
Yeah, thank you. Uh, Rupal, are you available?
Yeah.
Yeah, okay. Just a second, I'm sharing the screen.
Yes.
Can you confirm, is it visible?
No, it's not yet visible. Yeah, it's
Yes, we can see the screen now. So,
Uh,
team, best of luck, and we'll
yeah,
ask questions at the end, and you may, proceed with the presentation. Yeah, best of luck.
yeah, thank
yeah.
you.
Thank you. So, good evening, panel. We are here as Team Transformers to present the solution of the case given. The team includes me, that is Rupal Mittal, Dhrumin Patel, and Prateek Sawant. Please excuse us for the absence of Prateek as he is diagnosed with COVID positive. Next slide, please. Let's now start with the case synopsis and problem definition. The line diagram shows the supply chain for the organization and it would look like from factory to RDC to warehouses and finally to the customers. Now talking about the key facts that were given in the case, the manufacturing industry deals in three product categories, that is electronics, furniture, and home and kitchen products. Further, as shown in the diagram of current network design, the organization has three factories, four RDCs, and 15 warehouses in the area. In the further slides, we would be focusing on two major problems that is given in the case. Firstly, do we really need all the RDCs and warehouses or just the real line will suffice? Secondly, if we are changing the network, then what should be the most optimum location for the RDCs? Next slide, please. Now let's analyze the existing supply chain network. In the existing network, as shown in the diagram and table, insufficient replenished inventory at RDCs with respect to supply and demand side is experienced. And the reason we find out would be the insufficient allocation of the few warehouses to the nearest RDCs. As given in the table, we can see that the Bhagmari RDC and the Ghaziabad RDC is being shortfulness of the inventory, and the Godhra and Kolhapur RDC is overloaded with the inventory. So we have decided to optimize this product. For this, we have used the Power BI, and we could see the inventory allocation in a more balanced way in the optimum form, where Bhagmari and Ghaziabad, the inventory or allocation of Bhagmari and Ghaziabad is increased, and the overloaded RDCs, that is Godhra and Kolhapuri, gets less loaded. As shown in the diagram, the optimized distribution network has the warehouses nearest to the RDCs. So this really helped to improve the existing distribution network. Further, for the optimized supply chain network, Dhrumin will take.
Yeah, thanks, Rupal. So let's now talk about the optimized supply chain network, which we have worked on. So majorly, as we can see from the Power BI model which we have worked here, so the four circles here show the clusters. So the clusters allocation is done majorly on the basis of the mean square distance method. So here, the basis or the focus area is that the central node or the node which is having a distance very less distance from the central node will be allocated the warehouse accordingly. So say for example we were having the Bagamari as a RDC, as you can see from the table which we have worked on at the bottom. So Bagamari RDC was been allocated with the warehouses of Andhra Pradesh, Assam, the Bagamari RDC own, and the Bihar. Same way other RDCs were being allocated like the Ghaziabad, Godhra, Kolhapur, and all these RDCs are included here. So our main focus was that minimum time must be there, and also the minimum cost of replenishment per kilometer must be ensured. And here we took the three parameters for the three bases, which is shown in the bottom figure, which is cluster allocation mapping criteria. So for the city, we ensured that the shortest distance and minimum time must be there. For the warehouse, minimum distance, low warehouse holding cost, and same way for the RDC, low storage cost and maximum service level must be ensured. So let's now look upon the what were the results of the we have found out from the inventory rationalization model. So here we can see that the matched and unmatched data, which is shown on the right hand side of the table. So what is this unmatched and unmatched data? Unmatched data is shows that in the optimized network model, the warehouses which were been found to be allocated to the RDCs, how much they were not unmatched with the ones in the existing network allocated in the warehouses and cities in the existing model. So majorly we found that 6% there was an unmatch. So here it concludes that the existing model which was given in the case was having a less efficiency, but after optimizing we were able to attain 100% efficiency here, thereby increasing the service level and also the customer satisfaction by decreasing the lead times. By looking upon the location planning for RDCs, here we have went beyond the case and thereby propose three methods how like how we can go for exploring the new locations. So first is the center of gravity method. So in this majorly the method is that the grid map is used, and in this grid map the weighted distances are being calculated. So the ones having the minimum like weighted distances, the location is fixed. In the second criteria, the location is based on the other parameters, like say for example the RDC or the warehouses must be near the seaports, or it must be near the logistic parks. So or we can allocate according to the demand also, like how the customer's demand is there. In the last method, we propose here the distance calculation according to the trial and error method, and the same calculation has been done as shown in the as shown in the bottom part. So we try to change the location of the Kolhapur RDC to the Telangana RDC, and after calculating the distances from the Karnataka, Kerala, Madhya Pradesh, Maharashtra, and Tamil Nadu and Telangana, it was found that the Kolhapur was having 4,400 kilometer total distance, and the Telangana was having a distance of 4,200. Hence, we say that Telangana would be a better choice for better efficiency and service level. So thereby, here we can extrapolate this whole method to the other IDCs and find out that which one would be the best. So now for creating the new network design, linear optimization model for the RDC selection and sizing was done. So now we have designed one framework here. So on the left hand side, the framework is shown, which says that first define the problem, right? So the problem was that we have to decrease the cost of the transportation, and also we have to decrease the distance. The constraints here mainly were that the demand of the warehouses must be greater than the actual demand of the customers, right? Because we don't want that the scarcity or the deprivation of the customers, like customers are not able to get the products as per the time, and hence we must ensure that the warehouses are having the ample amount of stocks in their storage. After that, we ran the optimization model through the usage of the Python v3 version, and we obtained that the Bagamari RDC, Ghaziabad, Godra, and Kolhapur. Say for example, Bagamari RDC. So the Assam, warehouse would be fulfilled by the Bagamari RDC, while say for example for the Godra would fulfill the demand of the Andhra Pradesh and the Bagamari RDC. So same way this whole extrapolation is done, and we have found the optimized network for the case given to us. And also we also came to know that how the cost of estimation of the transport mode can be done. So in the figure which is shown in the bottom left hand side, so the framework is that select the product category like the furniture or the electronic item or the kitchen which was given, then the total demand at each city is calculated, then the cost per kg by different mode of transport, like it was given that by Bolero pickup, or we can say using the 14XL or MXL or SXL vehicle, and then selection of the best mode according to the FTL mode must be done. So at last, now we would like to summarize our solution and the workings which we have done. So firstly, as Rupal said that in the optimized model, the northern RDCs, first of all, the uniform distribution was there. So northern RDCs were given more increase in net volume, and the certain ones were been relaxed with their loads, because in the existing model, uniform distribution was not there. Also, in the cities which were having a low demand, we can use the smaller vehicles to reduce the transportation cost, like the Bolero or the 14 feet XL vehicles. Also, as I said about the terms like unmatched warehouses. So in the unmatched warehouses, we found out that 6% inefficiency was there. and hence after optimizing we were able to increase the service level and efficiency. Fourth point says that the RDC's locations, as I said, that we have proposed other methods like center of gravity, sales demand, availability of seaports or other facilities nearby. And next one is that we know that factory produces products, right? But the demand is not always equal to the ones which are produced. Hence, we need warehouses for the storage. So consideration for the warehouse handling cost for certain time period must also be considered, and it must be optimized. Next is that the delivery timelines of the different products. So we must take care of the delivery timelines because customer satisfaction is considering one of the factor as the lead times. So the less lead time, the customer satisfaction is more. And the last point is that the company must not focus only on the logistics and handling, but it must also look upon the other factors like increasing the service level through the lead times also. Hence, these are the references which we have used, or we have also attached the Excel working, and we also have the Python like code which we have written in the notepad here. And thereby we end our presentation by giving a thank you. And now we are open for any question which you have. Thank you.
All right, excellent presentation, guys. I do have some questions.
Yeah,
So
sure,
first
sir.
of all, before we go into the questions part, I would just like to mention that you have done a real out of box thinking here because when we talk about the network design, it does impact the inventory storage as well, and it does impact other areas as well, which you have considered.
Exactly.
I also like the idea wherein I don't know on which nodes, I don't remember, but in certain nodes you have compared the replenishment versus the demand, hence identifying which warehouses are holding more inventory than the demand and which one are shortfalling. So that was excellent work. That is something which in situations can drive the whole study.
Exactly.
Uh, could you explain if you can share the slide again and could you explain a little
Sure,
bit
sir.
more about that matched, unmatched part? I'm not sure if I'm clear
Yeah, yeah,
about it.
sure, sir. Just a minute. Sir, is it visible, the slides?
It is, yes.
Yeah. So, sir, here, majorly, so this is the example of the sample, one of the sample which we have calculated, right? So this is a snippet of it. So this row or this column shows the existing networks allocation, like warehouses and the cities. And here it shows that how the RDC allocation and the warehouse optimization is done through the our optimized network which we have worked on. So here we can see that how the difference is there with the warehouse optimized which we have given and what the warehouses which in the existing model was there. Hence, we use the if condition here. And in the if condition, if the match is not there, then it shows that unmatched data. And if the match is there, then it shows that matched data. So here we can, let me put the pointer here, just a minute, sir. Yeah. So, sir, this match, we came to know that some of the net volume was around, we can say, 39.4 lakhs, and unmatched data was around 2.51 lakhs. So, after calculating share, we came to know that unmatched data was around 6% and the matched data was around 94% in the existing model, which was given in the case.
Okay, got it. Got it.
Yes.
So you did the realignment here. You realigned the warehouses to the correct replenishment center
Yes.
and tried to identify. Good work. Okay.
Yes,
And
sir.
can you now go into the part wherein uh, you were doing the clustering and you were identifying three different methods. Yeah, this one.
Yes, sir.
No, not this one. The one wherein you had three different methods for identifying the.
Yes, yes. Exploring new location. Yes.
So now when you mention these three different methods, what did you
Hmm.
do exactly? So you did a center of gravity analysis, then did you validate it on these parameters or did you use any one of these three methods?
No, sir. This is the like we have proposed the methods which we can use for further like exploring. Actually, we have used the linear programming in the Python only, but these are the three processes which we, after research, we came to know that we can use this. Actually, we haven't used these processes. We just use the like one of the calculation to show that these processes also exist. Like say for example, this third option is there, optimized distance calculation. So here it shows the Excel one. So we try to use the data from the case and got to know that how we can apply this trial and error method here. So what we did was that we shifted the Kolhapur warehouse to the Telangana, and after found the total distance comparison. So here we can see that 4,442.89, and yet Telangana approximately 4,200 was coming. So we came to know that by this also like warehouse can be obtained. But actually, sir, we have used the this just a minute. We have used the Python version here, sir. That's it.
Okay.
For
Okay.
the linear programming, we have used the pulp modeling, which is part of the linear programming model.
Okay. And anywhere in this presentation, did you show the comparison between the current cost and the to be cost, or how many warehouses would be open, how many would be closed, or how many realignment has happened?
So realignment, we just did the analysis was been done here, like how much, like how we can realign or we can shift the warehouses from Maharashtra to the Rajasthan, like for a particular case.
Okay. And
Yeah.
in your outcome, did you find out that any particular warehouses should be closed down?
In the output, sir, we just found out about the match and unmatched data. So we didn't got about this like which one to open, which one to close. But sir, if you give us time, we can use these three methods which we have proposed, and I'm sure that we will get the answer regarding it.
No, that is fine. So the
Yes.
idea of this whole case study was not to judge how accurate your solution is, because that largely depends on what kind of processes you're using, and
Yes.
there's a lot of experimentation that goes into these processes. So that is totally fine. What I wanted to understand was so the idea was very clear, that what kind of thought process would you have and how would you approach problems like
Yes.
this,
Yes.
which I really like. One particular feedback for you is, whenever you work on certain case studies, whether you realign the demand to certain warehouses or you close certain warehouses, or, in future, maybe you open
Yes.
certain additional warehouses, it is always and always advisable to compare your current scenario to your future scenario to understand what kind of differences are we talking about. Um, One more point from my side. So, after you complete your studies and you would go to different jobs and everything, you would realize that whenever you would do this study, from a practicality point of view, this is 50% of the work that is done, because now all the scenarios that you would provide would be operationally validated. So there would be a team who would validate it operationally and understand the feasibility of the solution that you have provided. This would help you a lot, because in general tendency, the analyst would think that, okay, fine, I would provide one solution and that can be implemented, which is not the case. So it is always advisable to put up multiple scenarios as an output with a comparison of all the scenarios with the as is scenario, so that the operational validation, whenever that happens, can pick and choose out of one such scenario. But all in all, very well done. We were only limited to network design part, but I can see that you guys have thought out of the box and thought about the inventory and the service levels, etc., which are driving factors in such studies. So good
Yes,
job.
yes, sir. Just one thing I would like to state here, sir. This was regarding the cost which you asked. So we have considered here the cost as a factor, which was a constraint here while designing the algorithm for in the Python. So, like we can see that how the arrangement or the allocation of the warehouses is taking not only consideration of the demand, which is stated here, but also taking into consideration of the total cost also.
Right, right. Yeah,
And total
because
cost, so this is about the total cost which you have considered the formula.
got it, got it. Good job, guys. Good job. So that's all from my side. I'll hand over to Franjali.
Yeah.
Thank you, Ritik. So yeah, very well done. Firstly, I would like to mention that I do understand that when you have a presentation and you suddenly you have 2 out of 3, it definitely makes a big difference. But I
No
frankly, I
problem.
can say that it did not really make that much of a difference when you all were presenting. So maybe that just gives me a confidence that you all were thoroughly involved in that. So it was
Yes,
not
ma'am.
dependent on the third person that he knows what he has to say. So that really did not show off in the presentation. So that's a good thing. And yeah, my second, I had two questions, and I think most of it Ritik covered. One was the match unmatch, because even I was a little lost on that front.
Okay.
And the second one that I had was that whenever you do a realignment of your warehouses, also your variable cost for your warehouses will also differ, because every
Yes.
this will be different. So I just want, that's what I wanted to understand, that how many did you close any warehouses after realignment? Have you actually checked how the costing differed for all the warehouses also? So that kind of was not very clear over here, but now that we've explained all of that already.
Okay, ma'am. Do you have any other question? We can clarify, like other than those.
No, these were the only two things. So for
Okay.
now, that is all. But in all, yes, it is good. And one more thing that I would like to mention is that yes, there are a lot of things that you've considered in the summary, which usually
Yes, ma'am.
when you're doing only a network design, this people would tend to miss, like the lead time, how much it should be, the customer impact that will happen to the last node, and all of that. But it is nice to see that you are taking a wholesome approach on the project. So that is something that is really good.
Thank you, ma'am. Thank you.
Thank you, ma'am.
So well done.
Actually, the case was very like related to the operations management, which we are currently studying, and it was very challenging for us also. But we used those frameworks, and we were able to like give the solutions here at the best.
Good job. Good job, guys.
Thank you, ma'am.
Pallavi, that's all for us.
Yeah. Thanks, team. Thanks for the presentation. And very nicely said, Ritik and Pranjali has mentioned many points. Thinking out of the box and team management, everything was great. And best of luck for your future. And maybe we can, proceed with the next team so that this event goes on. Yeah. Thank
Yeah.
you.
Thanks for the
Thank
panel, and
you.
thanks, Pallavi.
Thank you.
Yeah. Thank you.
Yeah, so we have the last team for the day, Team Dark Horses from NMIS Mumbai. All the best, guys.
Hello, team.
Hello,
Hello, can you
Hello.
hear me? Yeah. Hi.
yeah, we can
Hi.
hear you.
Yes, yes. So, best of luck. Go ahead, and we'll have some questions. I will definitely ask you at the end. I will not. We will not interrupt you in between. So you guys can carry on. Yeah. Thank you. Please start.
Good afternoon, everyone. First of all, we thank the organizing committee and the judges for giving us the opportunity to present here. We, the team Dark Horse, present the case based on a network design activity. Coming to the important fact mentioned in the case, that the manufacturing organization deals in three different product categories: electronics, furniture, and home and kitchen appliances. And they have three factories and four regional distribution centers and 15 warehouses. Each plant is restricted for production for one product only. Now coming to the problem statement, we need to find out that do we need all the RDCs or all the warehouses, or we can optimize the warehouse or the RDC connections as well. So next slide, please. From the given data, we have analyzed few segments. These slides represent the analysis of the revenue segment, and we will also discuss about. We will also present about our recommendation as well. So now coming to the table mentioned here, so we can see that out of 15 warehouses, we have segregated based on revenue, and 5 warehouses are collected revenue less than 1,000 crores. So these warehouses in Andhra Pradesh, Punjab, Telangana, Telangana, Madhya Pradesh, and Assam. Okay. So a few observation that from our side that we can't reorganize Andhra Pradesh and Telangana simultaneously because the city Telangana is directly connected to only those two cities, only those two warehouses. So only we can optimize one of them. And the second observation from this slides is along with that, we can also do some modification in Punjab warehouses because the Punjab warehouse is connected to only three cities, and that is and it is also collecting very less revenue. And those three cities can also bypass their revenue to other warehouses as well. And another one vital observation from here is Assam warehouse. Apparently, it is giving a very less amount of revenue, but apart from that, it is in a very essential location in Northeast because there are various location or various cities which is connected only through Assam. There are 9 cities even. Now, Vignesh will discuss about the volume analysis part.
Thanks, Ronak. So coming to the volume sales analysis, what we did was we analyzed the sales of different products from each warehouses and tried to find out which are the states which provide the highest revenue and volume. And we found out that the sales was very high in the Punjab one warehouse and the lowest was from Andhra Pradesh. And then coming to the monetary terms, we found out that and monetary terms in terms of product category, we found out that the home and kitchen products give out the highest monetary terms, and then the electronics has the highest monetary terms, and then comes the homes and kitchen appliances. And we also try to understand that the delivery types which are standard, premium, and same day delivery, we found out that 19% of the products were delivered on the same day, and 35% of the products have used a standard delivery. Next slide. So what we did was we consolidated all the data which was given to us with respect to the customer, and we made a sort of chain where we track the product from the customer end, and we since the chain goes from the factory to the warehouse, then to the distribution center, then to the customer city, we tallied all the data in one sheet and tried to analyze the distance traveled from the distribution centers to the customer states. And we found out that certain states serve a lot of states, and certain states serve very less amount of states. For example, if you see states like Kerala, Tamil Nadu, and maybe Uttar Pradesh relatively serve less when compared to states like Assam, Bihar, and Punjab. So we'll try to analyze which of these states can be maybe merged together so that we can reduce our costs, which will be discussed by Sadanand. The next slide.
Hello. Thank you, Vignesh. The selection of warehouses is a very important factor in determining the outbound cost of an organization. This is very important as it is a long-term solution, and it also involves significant fixed cost as well. And we did a primary cost analysis of the various warehouses which were available. The problem at hand was to examine whether the locations of the warehouses are optimal or not. We can see from the table that the total cost involved is very less for Assam, and the majority of the cost involved in the total cost, it comprises only of fixed cost. So naturally it will signify that that the location is not a very strategic location, and it does not involve much operations enough to justify the break-even point. However, as my friend Ronak explained earlier, Assam is a very strategic location, and it also helps us serve 9 cities as well. Moving on, we also did a distance analysis of the various warehouses. So what we did was I'll just show the screen also. Just a moment. Hello. Sorry for the delay. Like I got disconnected. So we did a analysis on the Excel. So what we did was we had various locations. We had the various sales data, and initially we did a data cleanup. So what we did in the data cleanup was there were several confusions in the names as well. For example, we had different names for Cochin, such as one started with CO, one started with Cochin, and one more name started with Kochi. And there were also several cleanups required, such as Pondicherry and Puducherry. So we analyzed a lot of data, and we consolidated the final data. And from the sales data, we matched the different products which are required using the product ID, and we calculated the different cost, the different volume, and the different weights which are involved. And we also multiplied that using the quantity, and to ensure that we get the total variable, we get the total variable cost and the total weights as well. And one more problem which we had was that the RDCs of the individual sales was not known. So what we did was we mapped all the different RDCs and to all the different possible locations, and we also calculated the minimum cost among them to find out. And what we noticed was that after consolidation, we found out the various average distances involved from each of the various warehouses to each of the independent states. And after analyzing that, we found out that among the different warehouses involved, we kept a threshold of 1,000 kilometers as a standard point. And we found out that, for example, we found out that Andhra Pradesh had about eight states where it transferred goods above 1,000 kilometers. And there were also some warehouses such as Kerala, which only had about six different states where it delivered distances up above 1,000 kilometers. So from this we can conclude that instead of a warehouse at Kerala, maybe we can relocate, and maybe we can relocate to a better optimal solution. For instance, we can locate it near Rajasthan, where it can help to reduce the workload as well. And this was our primary solution analysis which was done. Thank you for giving an opportunity, and we are now open for solution.
Okay. Right. Thank you for the presentation, guys. First of all, I really liked how you spent a lot of time on the analysis of the as a scenario. This is, according to me, the most important factor of any kind of study. So you need to spend a lot of time on the analysis part to analyze how it looks like. You also analyzed the warehouses on the basis of demand that they are catering to, also analyze them on the basis of sales revenue that they are bringing, and hence trying to identify if there is any warehouses that can be closed or that can be opened new as well. I don't think opening up the new warehouses was a part of the study, but that would definitely help you identify which warehouses can be closed. I also liked your idea about identifying the critical locations of the warehouses. So the warehouses which are at the critical location. So you identified, I think, two such warehouses which would not be closed because of their location, and hence you would now focus on the different areas of the warehouses. Uh, the main part. So till now everything is fine because you have done a lot of analysis on the warehousing part. However, whenever you're doing this kind of study, it is also important to do this analysis on the transportation part, how the transportation is impacting the total, movement from that particular warehouse. One good thing about this study was that the transportation, cost was pretty linear across all the vehicles that were provided. But they were different for different warehouses as well. So, for example, if there is a particular warehouse which has a lesser, fixed cost, might have a higher transportation cost associated to it. And if you decide to keep that warehouse open, that might invite a lot of additional transportation cost in picture. But other than that, excellent presentation. I like the analysis part, and good job done. Over to you, Frandy.
Thank you, Ritik. So I do not have any question as such, but yes, there's one point that I would like to mention that one of the key things that we usually always propagate when we are doing an analysis is the cleaning of the data that you actually receive and working or structuring and interpreting the data initially the first stage of it. So that is something that I found was really good in your presentation. So good job on that. Overall, it was a good presentation. I do not have any questions because Ritik kind of covered the transportation cost because that is what even I was. So Pallavi, that is all.
Yes, thanks, Ranjali. Thanks, Ritik. Yes, everything is almost covered. Well done, guys. I really like the presentation and all. And yes, over to Vrinda now. How we are going to proceed? We are going to take a break to make some decisions, and then we maybe get back again to discuss the.
At around
Yes,
5:20, if that is fine.
5:20.
30-minute break or yeah, whatever timing you guys are comfortable with.
Yes. So 30 minutes break. Yeah, 5:20 looks good. Let's just connect again at 5:30. 5:30. Yeah. Thank you. Thanks, everybody.
Thank you.
Thank you. Thanks a lot for the feedback also. We'll keep that in the next presentations as well.
Thank you. Thank you for your time.
Yeah.